We learned about how you can construct a singly linked list by setting its head to be the first node in a chain of nodes. And we learned about two different approaches for constructing such a chain. And make sure you understand both approaches, and make sure you understand the structure for the node class and also a singly linked list class. And now we're gonna talk about the different basic operations. Each one of them will be defined as a method, either accessor or mutator, depending on the nature of the operation. In total, we got about 6 methods to go through. Each one of them is pretty basic, and I also assigned some extra exercises to you. So you can definitely try to extend the source code made available to you. So if you go to this project over here, example string linked lists over here. So you will see under the string SLL package, you can see the singly linked list. I also put the comments over there suggesting what exercises you should be doing. That's actually consistent with what I suggested in the slides. All right, so that's something I will actually point out to you throughout the remaining of this week for the lecture. All right, let's now talk about the first one, the basic one, which will be to count the number of nodes in the list. If essentially we want to retrieve the size of the singly linked list. All right, so how do we know? How can we return the number of nodes currently stored in a singly linked list? Just return return an integer. All right, so I can give you a little bit hints, and then you can pause the video and think about how you may do this. You can sketch the idea on the paper before I go over the solution with you. And the hints will be, remember the fact that we actually kept mentioning, which will be only the last node in the chain of nodes has a null next reference. Only that. Every other nodes appearing before that actually got their next node reference to be not null, because it should be pointing to the next node. Otherwise, we cannot really make the relative positioning work. Right? That's really the emphasis we have been mentioning in the earlier parts. And you want to assume that this particular method that we're gonna define, it seems like it should be an accessor, right? It should be returning a number, and that should be defined in the context of singly linked list, meaning that we can make use of, the only attribute we can make use of will be the private attribute's head, which will be of type node, right? That's the implicit assumption we are making. All right, so now you can pause the video and think about how you might devise the solution. You don't need to go to the source code. The solution is already there. So I would suggest maybe just sketch on this piece of paper to see how you may write. Do you need a loop? Or you can simply get away from loop by implementing this solution. All right, you can now pause the video. All right, so assuming that you thought about it, let's now go over the solution, which is pretty straightforward. But I think the pattern there is actually quite reusable for many other basic operations. All right, that will be the method that we're going to define. But for the convenience of presentation, I simply ignored the keyword public. But you will see in the source code, every method we actually made, unless it's a helper method, otherwise it's going to be public, right? So it's going to be get size, which does not require any input parameter. We don't need it. We can just return. We can just simply count based on the head reference that's internal to the singly linked list. And it's going to return some integer. Right, the definition will be the remaining part, but let me now switch to iPad and then we talk about it. Okay. All right, so that will be the operation we want to talk about, and let's make the assumption that this is the singly linked list that we have constructed based on our understanding in the previous example, right? So we got a list whose head is pointing to the Allen node, which got Mark and Tom after that. And you can see Tom is the last node, whose next reference is actually null, right? That's the list you have been very familiar with. And this will be the fragment of code, like algorithm, to actually achieve the goal of counting the number of nodes. And what I will do is I'm going to talk about two cases over here. Whenever you want to design algorithms for linked list, you always want to think about at least two cases. Either the cases will be given to you, or you will be responsible for writing test cases yourself. Let me point it out. Case number one would be, can your algorithm handle empty list correctly? And case number two, obviously, will be, can your algorithm handle non-empty list? Non-empty list. And just imagine the following scenario. Let's say you're given this particular problem as an technical interview problem to solve. And let's say you're done with your coding maybe on a whiteboard in front of your future employer, and they will simply ask you, so how can you show that your algorithm over here is actually correct. In that case, you will definitely need to tell them that what your testing strategy is. In this case, you'll tell them that you will show them that your algorithm for get size is going to work, number one, on the empty list, meaning that it's going to return 0 for the size. And also, it's also going to work in the non-empty list case, in which case it's going to return 1, 2, 3, size 3 in this example list. So these are the two cases you should always actually try to show or try to test to really convince others that your algorithm is actually correct. All right, that's something I'd like to mention first. And all right, having this in mind, I would like to now talk about these two cases, and at the same time, I'll go over the code together with you. The code itself is rather straightforward. All right, let's now just go over very quickly. So we have some local variable size, right? That's going to be updated as we go over the chain of nodes. So presumably, it should be somehow initialized to be 0 at this point, and then we're going to start with the head. Every time if we are able to go to a non-null reference using the next reference, in that case, we're going to increment the counter by 1. So that will be increment by 1, and we go for the next reference, it will be increment by 1, and then in that case, oh, sorry, let me say it again. So the head over here itself is actually not null. That means we got at least one node, right? Starting with 0, so now the head is not null, so we say plus 1. And then if we are able to go for the next into a not null reference, that'll be another plus 1. And then this will be another plus 1, right? So that'll be a complete picture. So we got plus 1, plus 1, plus 1, so that'll be plus 3 in total. It's going to be for the non-empty case. But what about empty case? That's also something we want to handle. Right, so the local variable is going to do that thing over there, and let me just show you exactly where this local variable will get updated. It is initialized to be 0 over here, right? And then it will be incremented inside a while loop, okay? And you want to take a look at this while loop. It's really important to know, like, under what circumstances we're going to keep executing the body of the loop, and also under what circumstances we're going to exit from the loop. So these are the two questions you should always ask yourself whenever you see a loop. Okay, let's now do that. Now, if you look at the Boolean condition over here, right, you can see that it's telling you that if the current node, which is initialized to be the head of the list, that means that will be where we will start the traversing, right? I'm gonna visualize it when I trace it. And then we want to make sure that as long as the current node that we are looking at is not equal to null, in which case we're going to try to get to the next node for that particular current node, right? Imagine that if we didn't have this conditional check, in that case, if current happens to be null, and then you say null.get next, you're gonna get null pointer exception, right? That's one thing to note. All right, so that's you can think about, in some way, this is more like a guarding constraint to make sure whenever right before you try to say current.get next, is guaranteed there's at least some objects for you to invoke the get next on, even though current.get next may be null. In which case, when you go back to the loop condition over here, when it is actually equal to null, so null not equal to null is going to be false. So that means you're going to exit from the loop. All right. Let me mention one more thing, and then we'll do the tracing. So this part here also tells you that you will exit from the loop when the negation of this Boolean condition is true, meaning that the current is exactly equal to null. Right? That's we also did some exercise earlier to really analyze under what circumstances will the while loop actually exit. Right? That's something you want to make sure you understand. That can definitely help you when you do the tracing. So this will be the current is exactly equal to null, right? When the current is equal to null, that basically means this last node over here, when the current is set to be its next, in that case, it will be null. So once we get to this null here, we know that we should really terminate from the loop and don't go any further. If you don't have such Boolean condition set up properly, you may simply get an infinite loop. It's actually very important to know. All right, so now let's trace the code. I'm going to give you two cases, okay? So let's say case number 1. Let me just use a different color over here so you will see. Case number 1, let's use the empty list. Let me use the pink for that. All right, the empty list. Okay, let's now do case number 1. For case number 1, I didn't really draw that. Let me draw that right away. Do you remember how to draw an empty list? It's rather easy, right? So if you want to draw an empty list, let me put it here. Empty list would be the head of the list, right? Let me draw in a more simplified way, right? I don't really draw this entire box, right? I don't need to. You can think about the head reference of the list is simply pointing to null, right? So this is the empty list case. That's the simplest way to really visualize it, right? So this will be an empty singly linked list, right? So that'll be case number 1. We want to make sure our algorithm can correctly return 0 upon calling the method on this empty list. Let's see if that's the case, right? Let's now go over one by one. So what we're going to do is we're going to execute this line over here. Size will be initialized to be 0. Good. And then we're going to say the current is actually going to be assigned to head, meaning that current is going to point to wherever head is pointing to. So let's say current is also going to point to the null, right? Okay, I think this is not exactly accurate, but I think it makes sense. Why is not accurate? Null is not really an object. So in some way, I'm making that almost like it's like a reference aliasing. But just remember, you can think about head and current. At the moment, it's simply both are going to store different copies of null, right? But drawing that in this way is okay as long as you know what you're doing. All right. So after this line over here, we're good. And when we try to evaluate this particular condition over here, current is actually null, right? It is pointing to wherever head is pointing to, which is null. So current is null. Null not equal to null is going to be false. That means we don't even go into the first iteration, not even. And then we're going to return the size right away, right? So we're going to go to return the size right away. In that case, size will just be the default value, 0 over here. So this case is working. So I'll say check. Right? Hopefully you can see what I'm doing over here. I want to make sure not just that I can handle the non-empty list, but I can also handle the non-empty list. All right. And let me now talk about the non-empty list, which will be this diagram over here, right? So this will require a little bit of tracing. So I'm going to use a table over here, right? And in general, if you really want to use a table to trace, you want to find out the critical variable or critical expressions that you want to keep track of, maybe right before the iteration begins, and also during the first iteration, second iteration, and etc. Right? And for this particular tracing purpose, I chose the current, which will be this variable over here. Current is going to tell us about which node we are currently visiting. So the idea about the current is so crucial. I would say almost every algorithm, either a simple one or complicated one, of a linked list, either singly linked list or doubly linked list, you always need to have the notion about current. Keep that in mind. This one is so fundamental. All right. Let me just highlight it. And also, this one will be the Boolean condition. So what we can expect to see is it's going to be true until we see the false, in which case we terminate the loop. And also, this will just to tell us about which iteration we are talking about. I'll get there. And also, it will also be the size, right? Also the size, which will be the result that we want to return. All right? That'll be the idea. Let's now try to trace it, right? And what I will do is I'm going to now talk about basically case number 2, about non-empty list, which will be this non-empty list, right? The expected output should be 3, but let's see if that's really the case. All right, so let's now start with line number 2 over here. So size would be, let me just make sure I got the right color, blue. Line number 2, and we're going to initialize the size to be 0. And notice that the convention I have for my tracing table, I will go from left to right over here. So the initial value for size, we're just keeping in mind, is actually 0. And the very first one I'm going to put over here is going to be the size value at the end of iteration number 1. So that's why I don't put it just yet, right? Just my convention. If you got other conventions, as long as you're doing that consistently, you'll be okay, right? But in my case, I'm gonna go from left to right. All right. All right, let's now move on to line number 3. For line number 3 here, so this will be very important. So we'll talk about how we can initialize the current node over here, right? So current is actually going to be, let me use the orange to always keep track of the current. The current over here is actually going to be assigned to just the head of the list that we want to count the size of, right? So you can think about head over here is actually going to be this, right? The head is actually pointing to this particular node. And by the way, remember we said we are now in the context of the syncly linked list class. That's why you can get access to head directly. If you really like, you can definitely say this.head, but it will not be necessary. In this case, we don't have any clash with the parameter, right? That's something you also learned in the earlier Java course. All right, so now we know that current is going to be assigned to wherever head is pointing to. So that means current is actually going to point to here, right? That's how we initialize the first node to inspect. All right, so we're going to say head current over here. And you can expect that once the current has been initialized, it's going to move to the right after every iteration or at the end of each iteration. All right. And we're going to go on to check to see whether we should actually go for the very first iteration. We're going to check this Boolean condition, right? That'll be obvious. Oh, before that, so what's the current value? The current is really pointing to wherever Alan is pointing to, right? So in the table, I can simply say just Alan. Okay, it's initialized to be wherever Alan is pointing to. And then current is not equal to null. This will be true because current is really pointing to some node that exists in the memory. So that's definitely not null. So that will be true, right? Because it is true, we're going to go for the first iteration. So we're going to go into the first iteration line by line. And the first one here will be very, very crucial over here. And for those of you who might find this kind of difficult to understand, let me try to help you a bit. You might be struggling with the fact that current appear both here and also over here. It's actually a very common pattern for you to really move on to make some progress in the loop, especially for linked list. The analogy I can give to you will be, remember how we compute I is assigned to I plus 1, right? That's something you pretty much know how it works. In order to do this, you have to compute the right-hand side I plus 1 first to get some value, and then reassign that to I. Similar here. In order to do this variable assignment, you have to compute what current.getNext is, and then copy that reference into the current to override it. That's what's going to happen. Let's see what's going to happen here. So what's current.getNext? All right, so you can see current.getNext is pointing to this node over here, and then we're going to reassign current into this particular node. That means move that to the right by 1 position, right? That's what we're doing. So current dot get next is pointing to this node over here, and then we're going to reassign current to that particular node to the right, right? So current, rather than pointing to here, is actually going to point to over here. It's a very important update you want to keep in mind. All right. And then we're going to increment the size by 1. Initialize to be 0, remember? All right, so now size is actually going to be 1. So at the end of iteration number 1, the size value will become from 0 to 1, right? That's the complete tracing for the first iteration, all right? And then we're going to go back to see if we're going to do the second iteration. And for the second iteration, we're going to see current not equal to null. Current at the moment is actually pointing to mark. Let's now mark it, all right? So let's see, current is actually pointing to mark, right? That's what we did at the end of the first iteration. And indeed, mark node is not null, right? So current is not equal to null, definitely should be true still, meaning that we should go for another iteration. And that means we're going to go into the while loop, and then we're going to execute this part over here, and we're going to update the current again. Current will be reassigned to current.getNext. Current is here, .getNext is pointing to this node over here. So that means we're going to reassign current into this particular node to the right. That's exactly what we did earlier, right? Similar, very consistent pattern. So current.getNext is pointing to this node over here, and current is going to be reassigned to that particular node. It looks like we're getting very close to the end, but not yet. And after that, we're going to increment the size by 1. So that'll be the end of the second iteration. Size will be incremented from 1 to 2. And then we're going to go back to the while loop over here, the header, and then we're going to check again. Current not equal to null. Current is pointing to the Tom node over here, which is not null, of course. So that means it's still going to be also true. Right? So the current is actually pointing to the Tom node. So let me put Tom over here. And not equal to null is definitely true, as I explained. And then we're going to go for the third iteration over here, right? And the first line in the third iteration, we're going to, again, try to update the current. This time, what is current.getNext? Current.getNext is actually pointing to null. That's okay. We don't have null pointer exception, by the way. You only get null pointer exception if the current happen to be null and you're trying to invoke getNext. But now current is actually not null. But current.getNext is actually null. You want to distinguish between the difference. If you struggle, let me know. So current.getNext is actually null, and then we're going to reassign current to that particular null reference. So what's going to happen is we're going to get current rather than pointing to here. You can think about current is actually now going to point to null. All right, like that. All right, and then we're going to go on to the last line in the third iteration. That one is going to increment the size by another one, right? So that means at the end of the third iteration, size will be incremented from 2 to 3. And we're going to go back to the while loop for the fourth time, right? And we're going to evaluate current not equal to null. So current is currently null. Null not equal to null will be false, right? So the current value is actually null. Right? It is really pointing to null, as you can see over here. It's so important. So let me just highlight it. So that means we are basically done, because we cannot just keep looping. In that case, we'll definitely never terminates. And then we're going to, since it's actually current not equal to null, it's going to be false. So I'm going to put false over here. That means we're going to exit from the loop. So we're going to exit from the loop and then return whatever value it is for the size, which will be 3 over here. So that'll be the complete tracing for the 3 iterations that we need to do, right? So now you can also see kind of like what the running time is. The running time should be somehow proportionate to how many nodes there are in the list, right? That makes sense. Since the only way we can calculate it is to start with the head and then go for the next until we actually reach the next one, until we reach to the node where the next is actually null. So it's going to be obviously linear time, right? So definitely you really want to look at, if you want to look at the running time over here, which I also included in the slides, you really want to think about for the running time. Let me make some remark over here. We know that, okay, starting from first node in the chain, we keep calling getNext, right? We keep calling the getNext the getNext method over here until, sorry, I'm running out of space. I'm gonna continue from over here until reaching null. Right, so the idea, so the running time will be, well, calling just the getNext itself, just this one over here alone, will be a method call. But that one there is just to get a pointer, pretty much like attribute access. So this one here alone will just be bigger of 1, just this one. But now we want to think about how many iterations there will be. The number of iterations will be corresponding to exactly how many nodes you have. You can see iteration number 1, iteration number 2, iteration number 3, basically, right? All right, reaching now. So that will be n iterations. And each one of them will be constant. So n times 1, so that'll be big O of 1. So overall, it's going to be big O of 1. Right, so that's a running time that you also need to know how we can derive, right? Right, we are only approximating the running time. If you really want to know precisely how many primitive operations there are, you can also do that as an exercise if you wish. Right? I think for this exercise, pretty simple. I think maybe I wouldn't go to Eclipse to show you how to use debugger. We have a similar problem in the next part, in which case maybe I can use the debugger to show you quickly about how you can trace such basic operation, just to get some better idea, more insight. All right, let me go back and finish off the slides. That's the code that we have gone through is only a very small number of lines, but I think there are quite many subtle details over there you simply just cannot ignore. You have to make sure you understand them perfectly. Otherwise, when you actually see any more advanced problems which you are required to solve, you wouldn't be able to do them. So you want to make sure you understand very well about how to use the current and also how to declare some local variable and update it in each iteration. That's the main pattern I want you to learn perfectly. And that's also the critical question whenever you see a while loop. Always ask yourself, under what circumstances would you exit? That should be exactly the logical negation of the Boolean condition over here, right? And remember, when we talk about insertion sort tracing in last week, we also talked about if you actually got some compound Boolean expression as a Boolean condition, maybe conjunction. In that case, taking the negation will be like you got to apply De Morgan, right? That's something you want to keep in mind too. Right, so what about the running time? Well, as we explained, it's going to be big over n. And you'll be now time to really contrast the counterpart operation in arrays. In the case of array, do we need to take linear time to really inquire about the size of the collection? The answer is no. All you got to do is to say array, for example, a.length. That will be just constant, right? You can see. Now, in this case, when we only got just the attributes for the head, from the singly linked list. In that case, inquiring about the size will unavoidably need to be linear because we got to start with head and go all the way to when we can see the null reference by the next reference, right? So you want to contrast these two performances clearly. All right, let's now move on to the next problem.